Hi, welcome to Light Utilage. In this session, I have taken another practice problem from theoretical yield. And the problem is if 34.8 gram of iron oxide reacts with 24.9 gram of carbon monoxide, they produce iron and carbon dioxide. The question says calculate the theoretical yield for metal iron. Well, to calculate the theoretical yield, we follow these simple steps. And the first step says that write the balanced chemical equation. And if we look at the problem, you can see that this is a chemical equation given over here, in which iron oxide reacts with carbon monoxide to produce iron and carbon dioxide. And this is a balanced chemical equation because number of atoms on both sides of the equation are equal. Here we are already given the balanced chemical equation, that's why we skip the first step. Now we move on to the second step that says to find the limiting reactant. It is the reactant which determines the mass of any of the product produced in the reaction. Well, before we calculate theoretical yield, we find limiting reactant. And the first step is to find the moles of these reactants. Well, in the problem, we are given the mass of these reactants. Here we have mass, that is mass of iron oxide is given, that is 34.8 gram. Here we have 34.8 gram. And the mass of carbon monoxide, that is given 24.9 gram. 24.9 gram. We convert the mass of this reactant into moles, and when we convert mass into moles, we use molar mass. That's why we look for the molar mass of these reactants. Well, the molar mass of iron oxide is 160, and unit is gram per mole. We divide these numbers to get moles of iron oxide. We use calculators. Well, the mass is 34.8 and it is divided by molar mass, that is 160. And this is the value we get, 0.2175. But we pick up this value with least significant figures. If we look at the mass of this reactant, you can see that the mass is given with three significant figures, 1, 2, 3, 1, 2, 3. That's why we pick up this value with three significant figures. 0 is a leading 0, that's why it is non-significant figures. 1, 2, 3 up to 7, we have three significant figures. We look at the digit next to 7, that is 5, and 5 is equal to 5. And that's why we round up 7 to 8. The value which we get, that is 0.218. Here we have 0.218 moles. These are the moles of iron oxide given in the problem. In a similar way, we convert the mass of carbon monoxide into moles. We use the molar mass of carbon oxide, that is 28.0, and unit is gram per mole. We divide these numbers. Here we have calculators, and the mass is 24.9 and it is divided by 28.0. This is the value we get. We pick up this value with the three significant figures, 0.889 up to 9. We have three significant figures. We look at the digit next to 9, that is 2, and 2 is smaller than 5. That's why we round up this figure. Here we get 0.889 and remaining digit becomes 0. Here we have 0.8889. These are the moles of carbon monoxide. Well, now we calculate the number of moles of these reactant required in the reaction by using mole ratio. Let's say we calculate the moles of iron oxide required in the reaction, and since we are going to calculate the moles of iron oxide, we pick up the moles of next reactant, that is carbon monoxide, and then we use the mole ratio. Let me show how. The moles of carbon monoxide are 0.889. Here we have 0.8889, and these are the moles of carbon monoxide. And we use the mole ratio between iron oxide and carbon monoxide in the balanced chemical equation. In the equation, you can see that 1 mole of iron oxide reacts with 3 moles of carbon monoxide. It means that the mole ratio between these reactants is 1:3. We multiply the moles of carbon monoxide by mole ratio. Here I put 1 mole iron oxide and it reacts with 3 moles carbon monoxide. We use the mole ratio in such way so that we could cancel the mole carbon oxide. And we can do the calculation. In the top we have 0.889 is multiplied by 1. We get the same numbers and it is divided by 3. Here we have 0.889 and it is divided by 3, and this is the value we get. We pick up this value with 3 significant figures. 1, 2, 3 up to 6 we have 3 significant figures, and we look at the digit next to 6, that is 3, and 3 is smaller than 5. That's why we round up this figure. Here we get 0.296. 0.296, and these are the moles of iron oxide required in the reaction. Now we compare the moles of iron oxide. These are the moles of iron oxide given in the problem, and these are the moles of iron oxide required in the reaction. When we compare these numbers, you can see that 0.218 is smaller than 0.296. It means that we are given less number of moles of iron oxide, but we require more number of moles of iron oxide. Therefore, iron oxide is a limiting reactant. This is how we calculate the find the limiting reactant. Well, we are done with the second step. Now we use limiting reactant to calculate theoretical yield. Well, since iron oxide is a limiting reactant, that's why we begin with the moles of iron oxide. Here we have the moles of iron oxide, that is 0.218 mole, 0.218. These are the moles of iron oxide, and we use the mole ratio between iron oxide and metal iron, because the question says that calculate the theoretical yield for metal iron. That's why we are going to use the moles of metal iron in the mole ratio. Here you can see that 1 mole iron oxide produces 2 moles of iron. That's why the mole ratio is 1:2. And since we are going to calculate the moles of Fe, we put the moles of Fe at the top. Here we have 2 mole Fe, that is iron, and in the bottom we have 1 mole iron oxide. Here we got the moles of Fe and we convert its mole into mass. Well, the atomic mass of Fe is, that is 55.8 gram per mole. I mentioned here 55.8 gram Fe, and in the bottom we have 1 mole Fe. Mole iron oxide are cancelled out. Mole Fe will also be cancelled out, and we will do the calculation. In the top we have 0.218. Here we have 0.218 and it is multiplied by 2, and so again we multiply this number by 55.8. This is the value we get. But we pick up this value with 3 significant figures, and in the bottom we have only 1. That's why we get the same numbers. 1, 2, 3 up to 3 we have 3 significant figures. We look at the digit next to 3, that is 2. 2 is smaller than 5, that's why we round out these figures. Here we get a 24.3 gram Fe. This is the mass of Fe produced in the reaction, or we can say that this is the theoretical yield. Theoretical yield is nothing but the mass of the product produced in the reaction. This is how we calculate theoretical yield, by using these 3 simple steps.